absent? Alex Yu. Amit Charan.
Present.
Yeah, I'm saying that. Alex Yu, where are you? Alex Yu, I'm here. Okay. Anjali Datta. Anjali Datta. Anjali Datta. Can you hear me, Anjali? Yes? No, but you have your audio is not working. Anjali, your audio is not working. But anyway, I can see Anjali Datta, but your audio is not working. You should double check that. Ariel Moskowitz.
Here.
Yeah. Okay. Arlie Evans Joseph. Yeah, I saw him. Yeah, I know him. Caesar. Caesar. Yeah,
Yes.
you have to be. Your camera should be ready. Your camera, if you do not fix it, I will give you one more day. That is Thursday. Then you will be marked absent.
I'm here, Caesar.
Yes. Okay. David Mejia.
I'm here.
Erin Desir. Erin. Okay, they will be marked absent. I'm very sorry.
No, I'm here, Professor. My internet stuff wasn't working. I'm sorry.
Okay, now your video, audio, and everything, they should be working, okay? Hugo Barahona,
I'm here.
James,
Here.
okay, Lindita Kalach,
Can you hear me?
yes.
Okay.
Anna Sebastian,
Yes, that's me.
okay.
Sebastian
Matthew,
Yes.
I'm here.
Mohammed Kabir,
Mic off.
Mohammed Kabir being marked absent, okay?
Professor,
Yes?
Mana Sebastian is here.
Where is Mohammed Kabir?
No, Mana Sebastian.
Mana Sebastian is here, but where is Mana Sebastian? You're not supposed to speak for Mana Sebastian. Oh, okay, I can see it. Fine, see you. Mohammed Kabir, okay, marked absent. Nathaniel Campos. Nathaniel Campos.
Yes, sir.
Okay, I guess. Mohammed Kabir, okay, I got it.
Yeah, I'm here.
Okay. Nathaniel Campos. Nazia Nusha.
Right here, Professor.
Good. Ricky Chen.
Yeah, right here.
Okay, Sebastian.
Mic on.
Sebastian F.
Yeah, I'm here.
And Sebastian John Bart.
Yeah, that's me.
Good. Shania Khan.
Hi, Professor.
Okay. Where is Shania Khan? I cannot see you.
That's me.
Where?
I think my screen is right next to you.
Okay, got it. Good. Shakila Khatun.
Here, Professor. I'm here.
Okay, good. Simon Lowe.
Oh, I'm here.
Okay. Stanley Lee.
I'm here.
Stephen Nola.
Here.
I know him. Stephen.
Steven is here.
I'm right here.
Okay. Timothy Moyes.
I'm here. I'm here.
Good. Victoria Cortez.
I'm here.
Wasif Khan.
I'm here.
Yunkong Ma.
Here.
Okay, now listen, Thursday, all of you should get your camera, video and audio ready. I would like to see, because that's very important. We don't have to do it every day, but till at least for the up to next week, say. And then, of course, during the exam. No question about that. So we've got some problems, very, very problems. We will go over the homework problems plus certain problems that I have. I will start by going up, but that's okay. You start from here.
Hello?
Hello? Yes?
Yeah, you call Steven, but there's two Stevens.
Huh?
You call for Steven, but there's two Stevens.
Yeah. There's two Stevens. Okay.
Which one did you call? Because I only heard one.
Now there are two. No, one is Stephen Nola.
But you didn't call
Stephen.
me then.
And then I called you, Stephen.
Okay, okay.
Yeah. Okay, now let us start with these problems. You remember last time we proved this. Recall. There is another question. Where is Anjali Datta? Anjali Datta. You sent me an email that you were not present in the first class. So I sent you the notes. Did you get the notes? Can somebody tell me, did all of you get the notes?
Yes, Professor. I
Okay.
don't.
Okay.
Yes.
Okay, but Anjali Doctor, please fix your audio. Oh, wait, there's another login who's Abu Bakr Akhtar. I don't know what can I say that he cannot log in. Okay, let us continue. Let's start. So recall AB inverse is B inverse A inverse. I told you last time. We proved this last time. Now, so let us consider this one. Simplify. So AC inverse inverse. AC inverse. AC inverse inverse. AD inverse. So this will be what? AB inverse is B inverse A inverse. So it gets, so C inverse inverse, that is C A inverse. This is A C inverse. And this is also C A inverse. A D inverse. Now you see what is happening. Matrix multiplication is associative. Oh, associative, not commutative. That's the fundamental point. So C A inverse A, C inverse C, A inverse A, D inverse. So that is C I D inverse. And C times I, it's identity matrix. So simply C D. That is the simplified answer. Next, let us take this one. AB inverse AC inverse D inverse C inverse inverse D inverse. So that is AB inverse AC inverse D inverse inverse inverse. So C inverse inverse D inverse inverse. So CD D inverse. That is AB inverse A. So that is I, this is I. So that is A, B inverse A. So this one, let's do this one. Show that A times A inverse plus B inverse. That is B. Oh, this is interesting. So A times A inverse plus B inverse. Then comes B. Then is A plus B inverse. So you see this should be A inverse distributive law plus A B inverse B. A plus B inverse. Now that is equal to A inverse is I plus AB inverse B times A plus B inverse. So that is I times B plus AB inverse B times A plus B inverse. So that is B, I times B is B plus A times I. So that is simply B plus A. And this is B plus A inverse. And that is I.
Mic off.
Oh,
Mic on.
okay. All right, so let us take these two matrices. I just wanted to show you something interesting. A is 0, 1, 0, 2. A is 0, or no, how did I write that? 0, 1, 0, 2, okay. This is the problem of using an iPad. And B is 3700. 3700.
Professor,
Yes.
could you slow down a little bit? I'm still copying the previous.
Oh, yeah.
Thank you.
Yes. Yes. Please let me know when you're done. For all students, please let me know. Yes? Which one? That means which one? Last line? Last line? Yeah, because what is x times x inverse? That is I. A plus B is a matrix. What do you get? A plus B times the inverse of A plus B. That's I. Are all of you ready? Now you see, when is a matrix a zero matrix? When all its entries are zero, right? When all its entries are zero. A matrix is a null matrix, a zero matrix when all its entries are zero. So A is not a zero matrix. B is not a zero matrix. But let's take a look at A times B. 0 times 3 plus 1 times 0, 0, 0, 0, 0. That is the zero matrix. This is amazing. It happens only in matrices. Doesn't happen in numbers. You take the product of two non-zero numbers is always non-zero. So here we can see the product of two non-zero matrices can be zero. So AB is equal to 0 does not imply A equal to 0 or B equal to 0. That is something to be learned from here. Next, A is 0, 1, 0, 2, okay? A is 0, 1, 0, 2. And B is 1, 1, 3, 4. B is 1, 1, 3, 4. C is 2, 5, 3, 4. Well, okay, what is AB? Is 0, 1, 0, 2 times 3, 2, 5, 3, 4. So that is equal to 0 times 2 plus 3 times 1. 3. 0 times 2 plus 2 times 3. 6. 12 plus 4. 8. And what is AC?
Professor, it's not as AC you wrote down.
Yes, AC.
No, the top one is not AB
No, this was AB.
because it's
This is very, very good. Very good observation. Excellent. Excellent. So this is AC. Very good. Thank you. And now let me do AB. Good. AB is 0, 1. An attentive student. Very good. 1, 1, 3, 4. I'm going to finish 2 by 2 matrices today so that we really start from Thursday. There's much to say. 0 times 1 plus 1 times 3. That's 3. Times 1 plus 6. Times 1 plus 4. 8. So you see, AB is equal to AC. And usually in numbers, what happens? When you have AB equal to AC, A cancels. If A is not 0, of course. A cancels, then B equal to C. But B is not equal to C, and A is not equal to C. Yeah, B is not equal to C, clearly, and A is not 0. So now, what is the conclusion here? Cancellation law does not exist, does not hold. Cancellation law does not hold. Hmm? Okay.
So cancellation laws do not hold in matrices.
For matrices, they do not generally hold.
Okay.
We should always say generally, yeah. I mean, accidentally they can hold, but generally they don't hold. Hmm? Okay. Now, so these are the things that I wanted to tell you. Solve. Let me put it this way. Wait a second. If I can push this a little, no, up to this one. Then maybe a little further, and then no, not this one. Okay, let me push this here. Okay, now you can see the screen. Now the question is, yeah, we will do these problems. Oh, these are very, very interesting problems. But before that, let us consider this problem, these two problems. Let us consider these two problems. When is a matrix symmetric? A matrix, a square matrix, of course. Up to Thursday, we will talk about square matrix. No, Thursday itself, we will talk about generalities. A matrix, I'm just writing MATX. A is symmetric, which we saw last time, if A transpose is equal to A. Now here is a very nice question. Find the value of A, small a, if this matrix 4 minus 3, 4 minus 3, A plus 5, minus 1 is symmetric. So A equal to A transpose. So that implies what? 4 minus 3, A plus 5 minus 1. If you take the transpose, what is the meaning of transpose? Huh? The rows become columns, right? First row becomes the first column, second row becomes the second column. So 4 minus 3, A plus 5 minus 1. That means what? When are two matrices equal? When their respective entries are the same. That means minus 3 to be equal to A plus 5. And that means A is equal to minus 3 minus 5. It is minus 8. You can take a similar problem for a 3 by 3 matrix. Why don't you do this? Find the values, this is a good problem. Find A, B, C, find the values of A, B, C if this matrix two, 3, 0 A minus plus 2C. Stop that noise. If you have a question, please ask. Yes, what is your question? Is symmetric.
That's like a little bit confusing.
What's your question? Hello? No, I don't know. Abu Bakr Akhtar, did you have a question? Okay, do this problem. Do this problem, let's see. So it's the same idea. It's a 3 by 3 matrix, but that's okay. It's the same idea, A equal to A transpose. A is symmetric. That means A is equal to A transpose. A is this matrix. 2, 3, 0. A minus 2B plus 2C. 5 minus 2. 2A plus B plus C, A plus C, 7. This, now take the transpose. So if you take the transpose, then this becomes equal to, rows become columns, no? So first row becomes the first column. So 2A minus 2B plus 2C, 2A plus B plus C. Second row becomes the second column. 3, 5, A plus C, 0, minus 2, 7. Now, if you equate, all the respective entries should be the same, right? So 2 equal to 2, that is okay. A minus 2B plus 2C is equal to 3. 2a plus b plus c is equal to 0. And just take some. Take this one. A plus c is equal to minus 2. That will be easy. A plus c is minus 2. Solve the system. Solve it. Let's see you do it. How do you do that? You multiply equation 2 by 2. What do you get? You get 4a plus 2b plus 2c is 0. And your first equation is a minus 2b plus 2c is 3. Add. If you add this to cancel out, 5a plus 4c is 3. A plus c is minus 2. So now you can solve this as two equations, two variables. You can solve. So how do you solve this? You multiply first equation by the coefficient of the second. So 1, multiply this by 5. So 5a plus 4c is equal to 3. 5a plus 5c is equal to minus 10. Subtract these two. Subtract this minus that. So c equal to minus 10 minus 3 minus 30. Then quickly get the value of a. A is minus 2 minus c. So that is minus 2 plus 13. That is 11. And b, I can get the value of b from here. 2a plus b plus c is 0. That implies b is minus 2a minus c. Minus 2a minus 22 minus c minus 13. That's it. Yeah, let's take the homework problems with this. Very good problems there as well. Let's take these homework problems. Find A in each case. If you are given 7A inverse is minus 3, 7, 1, minus 2. Okay. So what is the inverse of it? Remember, x inverse is x. So what is 7a inverse is 7a. So that means 7a is the inverse of this matrix. The inverse of this matrix. And now we know how to find the inverse of a 2 by 2 matrix. Well, first find the determinant, which is, so that is equal to, what is the determinant? 2 3 is 6, 6 minus 7, that is minus 1. 1 upon the determinant, 1 upon minus 1, times, these two change places, minus 2 minus 3, and these two remain the same with signs opposite, minus 7 minus 1. So that is equal to 2, 7, 1, 3. So that is my 7a. So 7a is 2, 7, 1, 3. So what is a? It is 1 upon 7. So multiply by 1 upon 7. It's a scalar multiple. That's that. Question?
Wait, why did it turn into a 2 when you multiplied it by the determinant, 1 over the determinant? Why did it go from
What is the determinant? Determinant is minus 1. So minus 2 upon minus 1 is what?
Yeah, but -3, -2, it went from -3 to -2. Shouldn't it just be
What is negative 1 upon negative 1? That is 1. What is negative 3 upon negative 1? That is 3.
Yeah, so why is it say 2? Or is that a 3?
I think he's asking about the row becomes column and the columns. I think.
No. Oh. That's what we studied last time. Right?
Okay, I
The
see what you
inverse of the
mean.
matrix.
I see what you mean.
If the matrix is A, B, C, D, then what is A inverse? We saw that last time. 1 upon AD minus BC, BA minus B minus C. Saw that last time. Okay, next question. Same thing, find A, 5A transpose inverse is -3 minus 1, 5, 2. This is a good question. You see, 5, we saw last time, we proved this last time, remember? A transpose inverse is A inverse transpose. Well, I don't need that. Let's see, I won't need that. I will do something else. Let me see. Yeah, I'll do this. You can do that, but let's see. So 5A transpose will be the inverse of this matrix. Inverse of this. And what is the inverse of that? So what is the determinant? -6 minus 5. So 1 upon -6 minus 5, that's -1. Then, yeah, 2 minus 3, 1 minus 5, minus 2, minus 1, 5, 3. Okay, so that is my 5A transpose. No? So what is A transpose? It's 1/5. So multiply each entry by 1/5. So what is A?
So now transpose both sides.
Good, very good. Transpose of that. So that is minus 2 by 5, minus 1/5, 1, 3/5. Good. Oh. Then another question is this question. I plus 2A inverse is minus 1, 2, 4, 5. So what is I plus 2A?
Then inverse both side and
Very good. Inverse both sides. So what is the inverse of this? What is the determinant? Minus 5, minus 8, minus 13, minus 1/13.
oh, it's 5 minus 2 and then minus 4 minus.
No, minus 5, minus 8. So minus 13, that's okay. Good. So 5 minus 1 minus 2 minus 4. Isn't that right?
Yeah, that's correct.
Good. So that is minus 5 by 13, 2 by 13, 4 by 13, 1/13. Okay, so that is I plus 2A. Remember, I plus 2A turns out to be this matrix, minus 5 by 13, 2 by 13, 4 by 13, 1/13. So 2A is minus 5 by 13, 2/13, 4/13, 1/13, minus I. I is the unit matrix, identity matrix is this. So that gives me minus 5/13 minus 1. So minus 18/30, 2/30, 4/30, 1/13 minus 1, 1 minus 13 minus 12/13. Is this right? So what is A? A is half of this. This matrix
Professor, shouldn't it be minus 14/13?
which one?
You wrote minus 12/13.
Huh? Which one? Which one?
If you did 1/13 minus 1,
1/13 minus 1. So 1 minus 13. Huh?
14?
Huh? 1 minus 13. How can it be 14?
12.
Minus 12. 1 minus 13. 1 upon 13 minus 1. Come on.
Professor, I have a question.
1 minus 13, that is minus 12 by 13. Yeah, wait. I will take the questions. Minus 9 upon 13, 1 upon 13, 2 upon 13, minus 6 upon 13. What's your question? Yeah, question.
You lost me in the right before you started doing all the math when you put negative 1 over 13. How'd you get the negative 1 over 13? Right under the I plus 2a when you did the first matrix, and then you just went straight to negative 1 over 13. How'd you get there?
What's the determinant? What is the determinant of this matrix? Minus 5 minus 8. Minus 5 minus 8, and that is minus 30. So it is 1 upon AD minus BC. Here's the formula. This is the important thing. You have to get used to this, to inverse of 2 by 2 matrix, because Thursday we will be doing inverse of 3 by 3 matrix. That's complicated. Check this. So that's, any other question? Any other questions?
No, not for me.
Okay, so this we can erase. It's an insult. And finally, you are given that A inverse is 2 minus 1, 3, 5. So what is A? A will be A inverse. So just find the inverse of this. So that's easy. That's what we have been doing so far. So what's the determinant? 10 minus 3. 10 minus 3. That is 1. That is 13. So it is 1 upon AD minus BC. 1 upon 13. And then 5, 2, 1 minus 3. So that's equal to 5 over 13, 1 over 13 minus 3 over 13, 2 over 13. Okay? There were 3 other problems on homework which I will definitely take. But before that, I want to go straight to I want to talk a little bit about orthogonal matrices right now. Later on, when we will study this in detail, no, this is not in vectors. Just bear with me. That's I haven't planned. If I get time, I would like to do Hermitian matrices. That's complex. Just a minute, please. No. Wait a second. This book doesn't talk about orthogonal matrices. Huh? Right. That cannot happen. Wait. That simply cannot happen. Hmm. Chapter 7. Very good. Yeah. So what is the definition of an orthogonal matrix? This is something very interesting. Ah. Hmm. Hmm. Yes. So here I will take it as this definition. So let us write this down. Definition. Of course, everything is square matrix so far, right? A square matrix, and last Thursday I told you what is a square matrix. It's number of rows equal to number of columns. A square matrix A is called orthogonal. Right at the end of this course, we will come back to this, by the way. It's called orthogonal. Very important. I want to tell you about the geometry of this. This beautiful geometry. If the definition, let's take this as the definition. A inverse is equal to A transpose.
Professor,
Hmm.
a square matrix A is always what?
It's called orthogonal.
Okay.
It's called orthogonal. Orthogonal. That's the definition I'm taking. A inverse is A transpose. What is the meaning of this? This implies, and is implied by A inverse is A transpose. But A inverse is the identity matrix. So A transpose is the identity. Very good. Let us now prove, at least you must prove this. Number one, the transpose of an orthogonal matrix is orthogonal. Okay, why is that true? So let A, so A is orthogonal. I want to prove that A transpose is orthogonal, isn't that right? Okay, that implies A transpose is I. That implies A transpose is I. Last time we showed that AB transpose is B transpose A transpose. Remember, AB transpose is B transpose A transpose. We saw that last time. So this implies A transpose A transpose is I. That implies A transpose is I. I will not do that. I will stop here. Stop here. Implies A transpose is I. Next, the inverse of an orthogonal matrix. Orthogonal matrix is orthogonal. This is interesting. A is orthogonal. So what's the definition? A transpose is A inverse. That implies A transpose inverse is A inverse transpose. But what is A transpose inverse? I did it yesterday, last Thursday, is A inverse transpose. Transpose. Hey. No. I want to show what? I want to show A inverse. I want to show that A inverse is orthogonal. Na? So I want to show that A inverse transpose is A inverse inverse. Now this is, what's the definition? A inverse equal to A transpose. Okay. What is it that we proved last time? Remember, A transpose inverse is A inverse transpose. Okay. Inverse transpose. So this is, oh no. I made a mistake. I took inverse on both sides. So A transpose inverse is A inverse inverse. Now I'm happy. And A, that does it, actually. That does it. That, yeah, A inverse transpose is A inverse inverse. That implies A inverse is orthogonal. A matrix is orthogonal if its transpose is the same as its inverse. Always remember that. If its transpose is the same as its inverse. This is beautiful. A product of orthogonal matrices is orthogonal. Can you prove that? Product of two orthogonal matrices is orthogonal. So suppose A and B are orthogonal.
Professor, are we going to have a break today?
Sorry?
Are we going to have a break today?
We'll start taking breaks from Thursday. Thursday will be a difficult session. We'll take a break on Thursday. Okay? We'll start taking break. Why? You want a break?
Okay. No, that's okay.
No, just, we will finish this quickly. Thursday, we will start talking about products of matrices and m by n matrices. There will be sigma, summation, there will be inverse, 3 by 3, inverse on 3 by 3. It's complicated. So Thursday, I will give you a break. Now let us finish this thing. This is easy, you know. Suppose A and B are orthogonal matrices. I want to prove that AB is orthogonal. So matrix is orthogonal if A inverse is A transpose. So I want to show that AB inverse will be AB transpose. Aha. So that is equal to B inverse A inverse. We saw that last time. But B is orthogonal. Therefore, inverse is B transpose. A is orthogonal. That is A inverse is A transpose. And that is AB transpose. And that implies AB is orthogonal. And finally, this is a very interesting result. And number 4, should I? No, we have not yet done that. Okay, so we have not yet done that. Okay, let me just give you 1 or 2 simple exercises. Just like this, say, determine whether the matrix is orthogonal. And if so, find the inverse. And if so, find the inverse. So let's take 2 matrices like this. Number 1, say A is 1 upon root 2 minus 1 upon root 2. 1 upon root 2, 1 upon root 2. And B is 1 upon root 5, 2 upon root 5, 2 upon root 5, 1 upon root 5. Do this problem, let's see. And also, this is a very good question. What conditions must A and B, just a minute, I will give you, must A and B satisfy? I'll give you time to copy, wait. For the matrix, first copy the problems when I give you to be orthogonal. A plus B, B minus A. This is a very good problem. A minus B, B plus A to be orthogonal. Okay. Now what happened? Wait. Okay. Write down these problems first.
Professor,
Mhm.
could you reread number 4? Determine whether the matrix is orthogonal and if what?
And if so, find the inverse.
Thank you.
So you can use any one of these conditions, okay? And a matrix is orthogonal if A inverse equal to A transpose, and or equivalently, A transpose is I. A transpose is I. So I think say number 5, that should be better. A is orthogonal if and only if A transpose is the identity matrix. So let us consider this matrix A. Call that A plus B. I'm doing number 5 first. What is A transpose? A plus B, B minus A minus B, B plus A. So A transpose is R. What does that mean? That implies and is implied by A plus B, B minus A minus B, B plus A times A plus B, A minus B, B minus A, B plus A is 1, 0, 0, 1. Do the matrix multiplication. That should be easy because that's why I chose this. That's why I used this definition. A plus B times A plus B. A plus B squared. Row by column plus B minus A squared. A minus B times A plus B. A squared minus B squared plus B plus A times this row times this column. This row times this column. B plus A times B squared plus B squared minus A squared. And then A plus B times A minus B. A squared minus B squared plus B minus A times B plus A plus B squared minus A squared is equal to, A minus B times A minus B. A minus B squared plus B plus A squared. That is equal to 1001. This implies, simplify that, A squared plus B squared. B squared plus 2AB and minus 2AB cancel. So you have 2A squared plus 2B squared. And here you see everything cancels, 0. Here you see everything cancels, 0. And here you have A squared minus B squared, A squared plus B squared. So 2A squared plus 2B squared is 1001. What conditions must A and B satisfy? That implies, it is implied by 2A squared plus 2B squared is 1. So the condition that A and B must satisfy will be A squared plus B squared is half. That's that. Let's take this problem. A is 1 upon root 2 minus 1 upon root 2. 1 upon root 2. Actually, A is 1 upon root 2, then minus 1 upon root 2. And then 1 upon root 2, 1 upon root 2. So determine whether this is orthogonal. Well, A transpose. So what is A transpose? Well, here we will not use that definition. We will use A is orthogonal if A transpose is A inverse. Let's just use both. And you will see then what's happening. What is A transpose? 1 upon root 2 minus 1 upon root 2, 1 upon root 2, 1 upon root 2. What is A inverse? A inverse, you see, so that A inverse is determinant of A is what? Half minus half. Half minus half. That is 1.
Professor,
Yes.
A transpose.
Just a minute.
You need to flip A transpose.
Yeah, you're right. A transpose is this. Happy? Now, what is the determinant of this? This is 1 upon 2 minus 1 upon 2. So that is 1. So, and now you interchange these two, then that remains the same. Yes, they are the same. So A transpose is equal to A inverse. Stop the noise, please. A is orthogonal. Can you do this problem? This is a similar problem. This one. This one. Do it, that's it. I'll give you some time. What I just did, yes. So let's do this problem. Yeah, this one. 1 upon root 5, 2 upon root 5. Sure. And then 2 upon root 5, 1 upon root 5. 2 upon root 5, 1 upon root 5. Okay. What is A transpose? 1 upon root 5, 2 upon root 5. 2 upon root 5, 1 upon root 5. And what is A inverse? What is the determinant? 1 upon 5 minus 4 upon 5. 1 upon 5 minus 4 upon 5. That is minus 1 upon 5 minus 4 upon 5. So minus 3 upon 5. So 1 upon minus 3 upon 5. It's minus 5 upon 3. Minus 5 upon 3 times 1 upon root. No. They're interchanged. Nothing happens. So it is not going to be. So that gives me minus root 5 by 3 2 root 5 by 3 2 root 5 by 3 2 minus root 5 by 3. Certainly not. A transpose is not equal to A inverse. Not orthogonal. Okay, let me finish the other homework problems and then we can Yeah, so let's do these other homework problems I gave. Just a minute. Number 1, solve these equations. 5x minus 6y is 1, using matrix, of course, matrix inverse and all that. There will be a trick in number 2. Good. Okay, so number 1, what is your coefficient matrix? So how does it work? It is AX is equal to B, and we know X equal to A inverse B. That's how it works, right? So B is 110. So now you have to find A inverse. So A inverse is 5 minus minus 6. So 1 upon 11. So A inverse is 1 upon 11, 6 upon 11, minus 1 upon 11, 5 upon 11. A inverse times B, let's do it together. And B is 110. So that is 1 upon 1 plus 60 upon 11. No? 1 upon 11 plus 60 upon 11. 61 upon 11. Minus 1 upon 11 plus 50 upon 11. 50 minus 1. 49 upon 11. That is X and Y. So your answer is X is 61 upon 11. Y is 49. But take a look at number 2. There's a trick there in number 2. 3x plus 2y is 9. 3x plus 2y is 6x plus 4y is minus 10. 6x plus 4y is minus 10. So that, remember one thing, AX equal to B, if this is the system, we'll do 3 by 3 matrix on Thursday, the same system. There also it could be written like this. And then what did we do? We multiply if A inverse exists. That was the way. So the point is if A inverse exists. And A inverse exists, we saw if and only if A is non-singular. A is a non-singular matrix. That means determinant of A is not 0. Hello? What is the determinant of A here? A is, the coefficient matrix is 3, 2, 6, 4. Determinant of A here is 12 minus 12. That is 0. So, A inverse does not exist. That means can't you find the solution? No, there will be infinitely many solutions. See, let me show you. 3x plus 2y is 9. So 3x plus 2y is 9. And 6x plus 4y is minus 10. 6x plus 4y is minus 10. Okay, divide throughout by 2. So you get, so this gives you 3x plus 2y is minus 5. So sorry, 9 cannot be equal to minus 5. So no solution. So the system is not solvable.
Professor, could you go up a little?
That's why actually I gave this problem. I wanted you to see a case where the system is not solvable. Next. X minus 6y is 6. Minus 5x plus 4y is minus 12. See, minus 12 minus 5x plus 4y minus 2x. Okay, then what is my coefficient matrix? What is the determinant? 4. Stop that. Please. 4 minus. Why should there be? Excuse me. Can you stop that? Because this is equating. Mute yourself. So 4 minus 30. That is minus 26. So A inverse is minus 1 upon 26. 4, 1, 6, 5. Minus 4 upon 26. 6 upon 26. Minus 5 upon 26. 1 upon 26. So A inverse B what is B? B is 6 minus 12. 6 minus. So that's equal to minus 24 minus 72. Minus 24 minus 72 minus 96.
Isn't it plus 72?
What?
Isn't it plus 72?
No, minus 20. Minus 24 upon 26. Minus 6 times minus 12. Minus 72. Yeah. So minus 30 minus 12. Minus 30. Minus 30.
Yeah, minus 6.
Minus 42. I cannot understand what you are saying. I mean, it's pretty obvious. This times that is minus 24 upon 26. Plus this times that is minus 72 upon 26. So this implies x is minus 96 upon 26. Y is minus 42 upon 26. That's it. Okay, just a minute. Okay, good. So that is all about 2 by 2 matrices. We have done a thorough work. Now listen, Thursday I will give you a break. Thursday's work will be a little involved because we will not only do 3 by 3 matrices, but we will also, I will tell you about the compatibility of multiplication for 2 matrices. So we will be talking about m by n matrices, so not necessarily square matrices. So under what conditions 2 matrices can be compatible for multiplication? This is a condition that the 2 matrices A and B are compatible for multiplication if the number of rows of A is equal to number of columns of A, is equal to number of rows of B. We have to study that carefully, very carefully. So Thursday will be basically matrix multiplication, because that will involve the sigma notation and how to find. We will see many methods of finding the inverse of a 3 by 3 matrix. So how to find the inverse of a 3 by 3 matrix? That is also very. That's also very important. How to find the inverse of 3 by 3 matrix? Just a minute, please. This is bothering me. Just a minute. Okay, stop this. I'll fix it later. Okay, good. So we end our discussion today with this. Any questions?
I have a question, Professor.
Yeah.
Solution 3, A transpose, isn't it 4651?
Which one?
The problem with just with
This is not transpose. There's nothing to do with transpose. This is about inverse.
yes, but A inverse is 1 upon minus 1 upon 26.
Yeah.
But A transpose is 4651.
Why transpose? We are not talking about transpose. We are talking about inverse. There's no transpose. We're talking about inverse.
What is A inverse?
This is A inverse.
Minus 4 upon.
This is A inverse. This is A inverse. You can see it here.
Okay, I miss a sign. Thank you.
Yeah. Okay. Any other questions?
Are we gonna have homework today?
No, because I have to teach new topic on Thursday.
Okay, thank you.
Yeah. Thursday I can give homework. Homework will be just review this stuff. We did lots of problems today. Okay? Any other questions?
Okay, thank you, Professor.
Thank
Bye.
you. Bye. Okay, everybody should have their video on Thursday. Video and audio. So, for example, where is Anjali Datta? I mean, I don't see most of you. All of you
I have
should
a question.
Yes.
Yes. Do we need to turn